Hi, we are going to be presenting the paper An Offline Metric for the Debiasness of Click Models. Um, the problem solved. There are key biases in click data that cannot be measured using the traditional evaluation metrics. These biases include position bias. Users tend to click more on the items at the top of the search results, regardless of their actual relevance. For instance, if the most relevant document is ranked lower, it's less likely to receive clicks. Trust bias. It is a Many users assume the search engines rank the documents perfectly by relevance, so they trust the top results without questioning their quality. And third is a selection bias, where since only the visible documents can be clicked on, documents at lower ranks or any subsequent pages, they rarely get any attention. So this skews the data set. So limitations of the traditional metrics are perplexity. While perplexity, it measures how well a model fits the click data. It only applies when the test data is similar to the training data. It fails when the ranking policies or the user's behavior change over time. And NDCG, or normalized discounted cumulative gain, this evaluates the relevance of the ranked list. However, it does not account for biases in the training data, and it leads to leading to misleadingly high score for bias models. So key challenges are the traditional metrics fail to ensure that click models generalize and well under uh, policy shift, uh, which occur when when the ranking distribution change. Uh, this is called the covariate shift. This makes it hard for the deploy reliable models in dynamic environments. So the proposed solution in the paper is the CMIP metric, which is the conditional mutual information with logging policy. So that detects the model's debiasness to improve the generalization and the policy shifts. So the dataset used is the MSLR Web 10K dataset. It contains 6,000 queries with 10 candidate documents per query, each annotated with a relevant score from 0 to 4 by human experts. So this is a real-world dataset and ensures robust testing of the click models, and as it simulates diverse user interaction. Synthetic user click simulation. Why simulation? Since we can't always access real user interaction, we simulate clicks based on the models used. Position-based models assume that scan documents from top to bottom, and the dynamic Bayesian networks consider more complex user behaviors, including satisfaction and abandonment. So the solution is debiasness in click models. We're defining debiasness. Debiasness of a model is if its predictions are independent of a ranking policy used for data collection, given the true relevance of the document. So this means that the model isn't just replicating biases in the training data, but it's capturing its true relevance. Conditional independence. Um, Debiases can be understood through conditional independence. For example, if the predicted relevance of a document depends only on its true relevance and not on its position in the ranking, then the model is debiased. What the importance of debiases? Debiases ensures that the click models generalize well, even when the ranking policies or the user behaviors change over time. So it's a foundation property for building consistent and unbiased systems. So CMIP metric. A CMIP is a metric that quantifies the mutual dependence between a model's predictions and the logging policy conditioned on the true relevance. So interpretation of CMIP is the high CMIP indicates a bias model that relies heavily on the logging policy, and a low CMIP suggests that the debiased model that bases prediction on true relevance. CMIP is computed using CMIP measures the divergence between the joint distribution of the model predictions and the logging policy versus an independent distribution. So this KL divergence is computed using the KL divergence, which quantifies how one probability distribution uh, diverges from another. A classifier is used to distinguish relevance predictions from bias and independent distribution. The classifier performance helps estimate the CMIP metric results. CMIP um, accurately predicts how models will perform on new ranking distributions, unlike perplexity and the normalized cumulative discounted gain. For example, a model that scores high on NDCG for one model might fail completely under another. CMIP identifies such cases by assigning high CMIP values to biased models. By using CMIP, we can select models that generalize well, avoiding poor choices that lead to high regret. So this CMIP metric generalizes to out of distribution generalization, out of distribution cases. The key findings of this paper are the improved generalization. CMIP correctly identifies bias models like DCTR, which performs well but fails on out of distribution data. And it assigns low CMIP metrics to those which generalize well despite lower non-discounted cumulative gain. For example, CMIP predicted better performance when a model trained under noisy Oracle policy but evaluated under a new Lambert policy. The broader impact of CMIP include uh, it has significant implications for search engines like Google and Bing and recommended systems like Amazon and Netflix. It ensures robust performance when ranking policy changes, improving user satisfaction. It has universal applicability. This metric works well across different user models like PBM and DBN and ranking policies. So it is a versatile tool for diverse settings. Paradigm shift. CMIP promotes a shift towards distribution evaluation approaches focusing on robustness and generalization rather than the individual predictions. So my teammate Tanisha is going to explain the implementation of the CMIP metric.
We begin by installing necessary libraries, including the datasets in sklearn and SM CMIP packages for the CMIP metrics. Once these libraries are installed, we import all the essential modules which we need for a neural network model and pre-processing and evaluation methods. Preceding that, we load our MSLR Web 10K dataset using this dataset library. And this dataset is structured specifically for ranking tasks. We convert it into pandas data frame to facilitate pre-processing. And we group it by a query to retain relationships between queries and documents. Next, we group the data by each query, prepare individual list to store query IDs and features and relevance labels. And we flatten the nested feature arrays to ensure uniformity. To handle variations in feature length, we identify the maximum length in each query and pad shorter feature vectors with zeros. This allows us to standardize feature matrices, which are essential for model compatibility. We continue by checking and adjusting the feature dimension for each query, and we pad or tourniquet feature vectors as needed. And this step is crucial because it allows us to process each document with the same feature dimension and which enhances compatibility across queries. Then we used a PBM model to simulate clicks by assigning probabilities based on relevance labels and position bias. Documents with higher relevance have a higher click probability, and those at the top of the list are more likely to be clicked. We generate binary click data by comparing random values to these probabilities, which provides a realistic dataset for training and evaluation. After simulating clicks, we initialize padded arrays for features, clicks, relevance labels, and click probabilities, ensuring all queries have uniform shapes. And we split the padded data into training and testing set using an 80/20 split ratio. Continuing that, we define this a neural network model with several dense layers and regularization techniques such as dropout to prevent overfitting, and the model is trained to predict clicks based on document feature. After training, we generate predictions on the test data to make these predictions compatible with the CMIP metric calculation. We reshape the predictions back to the original query format, and then we move on to implement the CMIP, where we use scale divergence to assess the dependency between predicted relevance and logging policy relevance, conditioned on true relevance. So the classifier Kale divergence class implements the Kale divergence, where a classifier is trained on two data sets with and without logging policy influence. This divergence score reflects the degree of bias introduced by the logging policy in the CMIP class, and we use this pointwise approach to calculate mutual information conditioned on the logging policy. So the pointwise CMIP evaluates bias at an individual document level, and finally we compute this CMIP on the predicted dataset by our model, and which gives us an overall measure of bias in a model's relevance prediction. And we get a score which is less than 0 here, and ideally a score which is less than or equal to 0 shows very less or no bias at all. Thank you.